Imagine this. You're in a spaceship that can instantly zip across the galaxy faster than light itself. Sounds amazing, right? But according to Einstein's special relativity, if you could do that, you might arrive at your destination before you even left. And worse, you could send messages back in time, create impossible paradoxes, and basically break the universe. Today we're diving deep into one of the coolest and most mind-bending ideas in physics. Why moving faster than the speed of light would cause time paradoxes. First things first. Why can't anything with mass go at or faster than the speed of light? It's not just a speed limit. It's the foundation of how cause and effect work in our universe. To understand this, we need to go back to Einstein's special relativity. One of the key thought experiments Einstein used this light clock. Imagine a clock made of two mirrors with a pulse of light bouncing up and down between them. Each bounce is one tick. If the clock is at rest, the light travels straight up and down. But if the clock is moving sideways at nearly the speed of light, from your perspective, the light has to chase the moving mirror. It travels a longer diagonal path. Since light always travels at the same speed, c, it takes longer for each tick. That means time itself slows down for the moving clock. This is time dilation. As you approach the speed of light, time dilation gets extreme. Your clock barely ticks while years pass for everyone else. And to actually reach the speed of light, you'd need infinite energy, because your mass effectively becomes infinite. That's why nothing with mass can hit the speed of light. But what if we could go faster? That's where things get really weird. To see the paradox, we need to think in terms of spacetime, the four-dimensional fabric that combines space and time, invented by Hermann Minkowski. In a Minkowski spacetime diagram, time is usually vertical, space horizontal. Light rays travel at 45-degree angles because we set the scales so c equals 1. Every event has a light cone. The future light cone is everywhere a flash of light from that event can reach. The past light cone is everywhere that could have sent light to influence the event. Causes must come from the past light cone. Effects go into the future light cone. Anything outside is space-like separated. No possible causal connection, because it would require faster-than-light signaling. Normal objects follow time-like paths, always inside the light cone, slower than light. Light follows the cone itself, no paths. But a faster-than-light particle, a hypothetical tachyon, would follow a space-like path steeper than 45 degrees. Here's the killer. In special relativity, the order of space-like separated events depends on your frame of reference. If two events are space-like separated, one observer might see event A happen before B, but a moving observer could see B before A. That's the relativity of simultaneity. For a faster-than-light signal from A to B, in one frame it's forward in time. Boost to another frame moving toward the signal, and the time order flips. Now the signal appears to go backward in time. That's the core reason FTL leads to time paradoxes. Imagine two spaceships, Alice and Bob, moving apart at high speed. Alice sends a tachyon message to Bob. In Alice's frame, she sends it forward in time. Bob receives it later. But in another frame, or if we have a chain, Bob can instantly send a reply tachyon back to Alice that arrives before she sent the original message. Suddenly, Alice gets a reply to a message she hasn't sent yet. Paradox. This is essentially time travel via FTL communication. Now, the most famous version, the grandfather paradox. You build an FTL ship, zip back in time, and accidentally, or on purpose, prevent your grandfather from meeting your grandmother. Then your parent is never born, you're never born, so who went back to do the preventing? The timeline becomes inconsistent. The universe can't have logical contradictions like this. Physicists call this a violation of causality, the principle that causes must precede effects in every frame. In relativity, causality is protected by the light cone structure. Break the speed limit, and you can create closed time-like curves or loops where effects precede causes. That's why most physicists believe FTL travel, or signaling, is impossible. It's not just hard, it would destroy the logical consistency of the universe. Of course, there are loopholes people have explored. What about wormholes, or Alcubierre warp drives that cheat by warping space itself? Some argue they might avoid paradoxes if there's a universal preferred frame, or if quantum effects prevent inconsistent timelines. But even those ideas face huge problems, like needing exotic negative energy, and many lead to the same causality issues. Tachyons themselves, if they existed and could carry information, would allow these paradoxes. That's why searches for them have come up empty, and most theories treat them as unstable or non-physical. So, to wrap up, faster-than-light travel doesn't just require infinite energy. It would let you mess with cause and effect, sending information to the past and creating impossible paradoxes like the grandfather paradox or the tachyonic antitelephone. Einstein's speed limit isn't arbitrary. It's what keeps time flowing forward and the universe making sense. What do you think? Could there ever be a way around these paradoxes, maybe with quantum gravity or multiple universes? Drop your thoughts in the comments below. If you enjoyed this deep dive, smash that like button. Subscribe for more physics explainers. Thanks for watching. Until the next time, take care.